Are you awake? It's after 5, and you're all still here. This is awesome. Good day? All right, sweet. My name is Ryan Boyd, and my Twitter handle is on there at the bottom. And I'm here today to talk about graph compute and the various strategies that you can use for graph compute with Neo4j. And I'd like to kind of say that's mostly like a survey of the different technologies along with some demos of how those technologies work. So first of all, Neo4j is optimized for what? OLTP. Neo4j is optimized for online transaction processing. It's really there, we build it as sort of your primary database. We didn't build it with the intention directly of it being used for graph compute or analytics or things like that. That said, a lot of customers and a lot of open source users do use it for those things, but that's not, kind of where our key architectural decisions are made. But you can do it. And so what are the different types of ways that you can do graph compute? Well, first of all is subgraphs. Graph compute on subgraphs where you kind of have an anchor node that you're starting at, and then you are traversing the graph from there, only touching a subset of the graph. Those work pretty well in Neo4j because that's the exact same type of thing that a query does. A query starts at a node or a set of nodes that it finds, usually using index, and then traverses the graph from there. That's what we're optimized for. So there are some algorithms built into Neo4j that do this sort of subgraph traversal. And then there is global traversal. A lot of people want to run algorithms like PageRank or like some of the centrality algorithms and things like that we're going to see. And these algorithms require that it touch every single node in the graph. Touching every single node in the graph is very expensive. So Neo4j isn't really optimized for this, but I'm going to show you some techniques that you can use to do it anyway. Let's start off by talking about subgraphs, by trying to query just a portion of the data as subgraphs. So there are a couple different things that you can do here. First of all, you can do in Cypher analysis of shortest paths. How many of you have already done this? Okay, a handful of folks. And you can also do the shortest path algorithms from a REST call as well. But there's a Dijkstra algorithm that is available via REST call, but not via Cypher currently. Obviously, I hope to push the things that are available only via REST calls into Cypher as well, because Cypher is where the future is at. So I'm going to show you a couple different demos, and those demos are going to use a variety of different data sets. And so first of all, I'm going to plug my own data set here, which is the Graph Your Network application, which basically allows you to log in with your Twitter handle, does a little OAuth dance, and then it loads in your tweets and a bunch of other tweets and your followers and people that you're following and more into a Neo4j Docker instance for you to then run. And a couple of the queries here are going to use that, but I'll encourage you to check that out as well, just to have some fun with that data. All right, so the first queries here are shortest paths queries, and I'm going to jump over into my browser here. So what I've done, and I have multitudes of Neo4j servers running here. And what I have done with some of these is loaded in a lot more than just my tweets and the tweets around it. But I've taken a bunch of other users and other things to make some of these queries a little bit more interesting. So here's one query here. And this query, I'm saying all shortest paths. So if you do shortest path, it will just return 1. And all shortest paths returns all the possible paths. Pretty obvious. And this is the shortest path between myself and a particular tweet. So we can see here, this is me at the top right, and I wanted to see the shortest path between me and this tweet down here. And this tweet, where are we? I have to expand it over here. This tweet is actually a retweet from Best NoSQL. And that retweet from Best NoSQL mentioned both Max and Best NoSQL. And it turns out that the shortest path for me, or paths for me to get there, are to go through my following of Best NoSQL and then to the mention, or go through my following of Max Tamarzi and then to the mention. But it basically shows how I can get to this tweet. To an individual tweet, it may not be as interesting. Between two users is a little bit more interesting. And then, because I did load a decent amount of data in here, I literally picked random usernames to try to find my path between me and those random usernames. There's apparently a user named Kevin. I have no idea who it is, but I just guessed random names. And for those of you who know Neo4j, there's a guy named Kevin that works here that's really awesome, so I just guessed the word Kevin. And so this is the shortest paths between me and Kevin. So I follow DataChick. DataChick follows Kevin. And I follow, this is David McLaughlin, and David McLaughlin follows Kevin. So those are the two different ways that I can get through to Kevin. And if I just did shortest path, it would just choose one of those. And I shouldn't be pluralized then. So it just chose one of those, and it showed to go through David McLaughlin. Sure, sorry about that. So really, I'm just saying shortest path and then putting a standard pattern as you might have in your match clause normally. Okay, so that's shortest path. Very simple query, accessible through Cypher, just using, everyone today is having PowerPoint crash problems. Like, literally 6 or 7 people I've seen this happen to. I don't know if they released an update, which is... Okay, now I'm zoomed in, but that's fine. Okay. All right, so I did show you these couple different shortest paths queries. So that's sort of a basic subgraph query. That's just literally starting at a node and trying to figure out how to get a path to another node, essentially, or a set of other nodes. The next kind of set of queries we're going to show is using the Legis graph by my colleague, Will Lyon. And the Legis graph is awesome. For those of you who did not attend the hackathon, basically it includes all of activity of Congress related to bills and sponsorship of bills and things like that for a number of the different congressional sessions. And so it's a really awesome data set. I loaded it into my Neo4j instance using this tool as an aside that Will built, which allows you to load multi-line Cypher scripts into any Neo4j instance, which you might have found to be problematic in the browser. Will built this pretty cool tool to allow you to do that, and I will figure out the name for you at the end if you ask me. Will did this as part of trying to build a CSV importer that makes it really easy to import data into Neo4j in a graphical format. All right, so with this data set, I'm going to show you another shortest path query between legislators. So if I hop over here, and basically what this data set is like I was saying, like bill sponsorships. So what we know about legislators is who sponsored a bill and then who are the co-sponsors. And we say that the co-sponsors were influenced by the sponsors, and you'll see how that comes up here shortly. Did I do that, actually? I want to do this in another data set. So I am going to start this up. Okay. I'm going to do that over here in a second. There we go. Okay, and I will show you the query again. Basically, we're saying, find me the legislator with the last name of Maloney and a first name of Carolyn, and up through 3 degrees of separation on the relationships, find me another legislator with the last name of Cochran and show me the shortest path. And this shows you something a little bit more interesting than the Twitter data. It shows you basically the bills. Like if I'm trying to find from Maloney to Cochran, we can see that Maloney voted on 2 bills. Not exactly the most interesting thing, but voted on 2 bills that Cochran sponsored those bills. And so it just allows you to see the relationships between different members of Congress. And we're going to see later with some algorithms on Spark how some of the algorithms allow us to determine who are the most influential Congress people. And I'm actually not going to show this directly, but you can see another example. We have a database here also of airports and the distances between all of the airports. And I wanted to find the shortest path between San Francisco and Missoula Airport. The guy, Will Lyon, that I talked about before is actually from Montana, and that's the closest airport to his house. Obviously, that requires a connection. You cannot fly directly. But this, basically produces a very short graph that connects, and maybe I will show it just so we have context for the next part here. But it connects between Missoula and one other airport, and no, I don't think it's going to be possible for me to copy this out here. Okay, I'm just going to show it to you as the compute demo or the larger compute demo. But it basically connects through one other airport. And so that's the shortest path, is one connecting flight. But obviously that shortest path doesn't really give you an indication as to how much time it's going to take or what the distance is or things like that. For that, you need other types of algorithms other than just counting the number of relationships here. So for that, we can use the Dijkstra algorithm. So the Dijkstra algorithm allows us to have a cost on each of these traversals. So in the case here, we have these 2 airports, and each of the airports have a distance property on the travels relationship. And on the travels relationship, we have the distance, and we want to compute the shortest path considering what the distances are. And so the Dijkstra algorithm, like I mentioned earlier, is not available built into Cypher, but you can actually call it directly through a REST API. And so this is what the REST API request looks like. So you can see at the URL that I'm actually calling and contains 197.909 at the end there. That is the node that I am trying to come from, the shortest path from that node to the next node that I'm going to specify here shortly. And then it's just basic HTTP stuff, our content type, username and password, and the machine. And then I'm specifying Dijkstra.json. And here's the contents of Dijkster.json. So we can see here in the URL that I was posting to, I had the node that I'm starting from. In the URL, or sorry, in the JSON document that I am posting, I have the node that I'm going to. And then I'm specifying that the name of the property, which identifies the cost of that traversal, is the distance. And the relationship is travels, and to do an outbound traversal. And that is the REST API call in order to run this. And then the REST API result looks like this. Not exactly human readable, but you can parse it. So the first thing here we have is relationships and nodes. And these are all based off of the ID numbers. And in the Java library, this is obviously much easier to work with than when you're trying to bounce back and forth to the browser. And in some of the, I think the R driver, for instance, has built-in calls for making these REST API calls. So, or built-in functions for making these REST API calls. But if I'm just doing it from the browser, I can do a query like that. And I am going to try to run this one. Have that in here. I'm going to. So to compare the two here, we're doing the shortest path based purely off of the airport codes. And that's just saying, and purely based off the relationship. So we can go to San Francisco to Missoula through RNO, whatever airport that is. What is it? Oh, I'm sorry. That's not very helpful. Thank you for calling that out. Okay, let's repeat that. So I can go from San Francisco to Missoula Airport through this RNO airport, which I don't know what it is. Reno, thank you. And then, so that was that query, and I'm going to have to see, let's see here. Get my cursor back. And now I'm going to show you through with the Dijkster algorithm. Basically, I hand parsed those results, and we will see what that gets us. And so it gets us through a different airport, and then we can see sort of the cost of this traversal here. So if I'm traveling to San Francisco to, does people know what BOI is? Boise? That would be a good guess. 522, and then the cost of going here is 254. So basically, 522 plus 254, that's the cheapest mileage distance to travel found by the Dijkster algorithm. All right. Now if I jump back, so that's a really basic algorithm that you can do, again, sort of the subgraph style algorithm that is built into Neo4j. But a lot of you probably want to do more global algorithms. So there are a couple different ways to do global algorithms. You can do Neo4j extensions. There is a graph processing extension that is built by our friends at GraphAware. Graph processing extension that is built by Max and Michael. And then there's the GraphAware node rank algorithm, which just does page rank. So those are two different Neo4j extensions that you can use. And then there's the Spark integration. So this is, what I'm talking about here is Maze Runner, which is built by Kenny Bastani who is actually giving a session right now up there somewhere. And Maze Runner basically allows you to run Spark jobs and GraphX jobs on top of your Neo4j data. Maze Runner is actually implemented in part as an extension as well, so that's kind of the point at which these all hook into. So there are some concerns with how we run these. First of all, most of these global algorithms are batch jobs, right? So these algorithms aren't going to have real-time results that you've come to expect from Neo4j, just because they're too computationally heavy and sometimes too read and write heavy. But what we can do is write back the results from these algorithms back to our Neo4j data store so that then we can make real-time queries from those results. And that's what folks typically do. They compute the results off of their data, put those results back into Neo4j, and then use the graph to make real-time decisions. There is also a computation performance challenge here. In particular, you don't want to interrupt your real-time processing of your database. Your database is handling live transactions. It's your master data store. You don't want to interrupt that. So you have a couple different choices. Some folks actually create another node in their cluster specifically for analytics. And that node is synced, and then they can take that node and run these analytics queries on that node, either through extensions or over to something like Maze Runner. That's a possibility. The other possibility is using an extension that's a little bit smarter and only runs when you don't have much transactions occurring in your database. So that's what the graph-aware folks have chosen to do with their node rank, is just run it when the database is not under heavy load. But although there are these cautions, there is a great benefit that you get out of these integrations. In particular, Spark has a great community of people that are building different algorithms with GraphX on top of graphs, and you can take advantage of that if you're using Spark, for instance. And I covered those points. So I'm going to give you a little quick tour of Maze Runner, which is Kenny's project. This was Kenny's child. He actually turned his child over to Neo4j, I think officially yesterday. So we are now going to be maintaining this project going forward. We're, of course, looking for a lot of feedback. It's on GitHub. It's open. Take a look. Send us feedback. Let us know what you'd like us to work on, what you'd like us to prioritize, and we'll definitely take that into consideration. So Maze Runner is based off of Spark. Spark is all about in-memory, large-scale data processing. And it uses Spark's GraphX, which is their API for graph processing. And this is the general architecture of how it works. So we can see here at the top left here, we have Neo4j. Top right is Apache Spark. Basically what happens is you do a query on Neo4j. And we'll see that here shortly. You basically call the Spark extension. It takes data out of Neo4j and gets that data through Maze Runner copied into HDFS. And then Spark and Maze Runner then read that data out of HDFS, do the processing on it in memory, and then takes the results and writes them back to HDFS, and Neo4j picks up those results through the extension. So it's basically a combination of a couple different messaging queues, and we'll see how that works with this live demo here. It did switch to mirrored displays this time. Okay. So if we go into my terminal here, I am going to shut down this other instance, which is running on the same port. And basically what I have here is the kind of vanilla installation of Maze Runner. And the vanilla installation of Maze Runner is using Docker Compose. You can, of course, run this outside of Docker, but this was the easiest way that Kenny found to explain this to everyone. And it uses Docker Compose, and it basically combines a couple different Docker images. It combines an HDFS node, and it combines the Maze Runner image itself and a Neo4j database. You can see that all there, as well as the ports that the Neo4j database is mapped to. Volumes here is pointing to the actual volume that my Neo4j data is stored on. That's not in the container because the container doesn't persist. It's on the host machine. And then we're specifying links from the Neo4j to Maze Runner HDFS that basically allows network communication to occur between the two of those, for those of you who aren't familiar with Docker config files here. So I'm just going to say Docker Compose up. And all it's doing is reading that file, and it is saying that I already have that port allocated, which I thought I just shut down. Oh, I need to exit out of this. All right. So I'll wait till that stops. Just going to remove it so I can show this in a clean state. Okay. So I'm going to say Docker Compose up, and it basically is going to start each of those containers, the HDFS, the Maze Runner, and the Neo4j container. And we're seeing the console output here of them combined. And he did some nice ASCII art, as you saw. A lot of people put a lot of effort into ASCII art. I don't know if there's any awesome tools that take images and make them into ASCII art, or if these people are doing them by hand, but anyway, that's pretty intense ASCII art. All right, so now it's basically starting up Neo4j, and we can see a standard message at the bottom here saying Neo4j is now available. And I started up on the same port and IP here, and we can see the data that's in our Neo4j instance. I am going to show you that we have nothing to start with. So this is basically querying, finding the legislators where they have a page rank, and matching those that are in the Senate and returning them. And this should return nothing right now because we don't have any page ranks. And there are no rows returned, as expected. But now if I go over here, and we can see, it's sitting at this steady state, there's no output. If I go over here and tell Maze Runner to get this URL, forget which one, there we go. So this is just doing an HTTP GET from within the browser with all my auth credentials and all, and saying to run PageRank, that's the algorithm, that's the part of the path which indicates the algorithm, and use the influenced by relationship, which is that sponsor-co-sponsor relationship. And actually, I should show you over here what's actually happening. So the call got made. And you can see here at the top, it exported the data out of Neo4j. So you see records exported, 20,000, 40,000, 60,000. So 100% exported. And then what's happening here is Maze Runner and Spark are doing their work and outputting all their logs, which is a lot of log data that's outputted here by default. And this will take a little moment or two. And it's time for me to actually mention something here. In terms of computational heavy analysis. So PageRank isn't that computationally heavy. There are plenty more computationally heavy algorithms. The computationally heavy algorithms may be better with something like Spark, where you can distribute the processing across many different nodes, combine the results together in a distributed file system like HDFS, and then load those back into Neo4j. Very much like, Maze Runner and the concept of using Spark may be better for that. We're going to actually see here shortly, though, for algorithms like PageRank, it's actually a lot faster to do it directly in Neo4j. This is kind of the old thing of sometimes an Excel spreadsheet is actually faster than Hadoop. That's actually true in many times. Depends on the size of the data and your computation. So anyway, here we can see our job was completed, and we can see here, let's see. Actually, I'm not sure where that is, but the data was written back to HDFS, and the job was complete as it was loaded back into Neo4j. And so now if I run this match statement again, which is again is just matching the legislators that have PageRank and ordering them by their PageRank. And we can see here that Orrin Hatch, as a senator, has the most highest PageRank. But if we actually eliminate this Senate restriction and just return all of them, pretty much every, actually, I shouldn't have eliminated that, I should include the body, but you can see actually the page ranks here for the House of Representatives are actually much higher because there's a much larger body for them to influence bills on than the Senate. So I think it comes up to like number 200 before you get to senators in terms of the ranking of the page rank if you include both of them together. All right, so that was doing it with Spark. And now I'm going to shut down Spark here. And it's really easy to shut the things down, just as I started them up. And I am going to start this instance back up again. Once this is down, good. And this instance has a Neo4j extension in it. It has the extension that does the graph analysis by Max and Michael. And it is starting up here, and now I can run it. All right, so this has that extension in it, and this has the calling of the extension. I have a URL over here. Again, the extension uses the same sort of mechanism for calling it. Basically, you can make an HTTP request to call it. So in this case, I'm going to do it as curl, but I'll show the database here first. Okay. And it completed PageRank. And it completed it that quickly. Now if I run the same queries here, the results are slightly different. I don't know if they did the same number of iterations. I didn't look at that. But if you consider how fast that worked versus how fast Spark worked, there is sometimes an advantage of doing things just in the database. But to give you an example, I tried to do a betweenist centrality algorithm earlier today, and on Spark, giving it only one single CPU of one machine and all of that, it was taking hours and hours and hours. It might be better that that be done in Spark rather than taking that much time inside Neo4j. But so if you have more computationally heavy algorithms, I can see how using Spark would make sense because you can actually parallelize that out to many machines. And I am going to hop back here. You know what? I am going to show you the betweenness centrality. Oh, sorry, not betweenness, the closeness centrality. Yes, the curl command. You want to see that? Yeah, so once you install the Neo4j extension, then this command exists. And it's basically you copy 3 files into your plugins directory, and then you add one line to your Neo4j server properties. And then once you do that, you can run this command. And it basically, all this is doing is calling that extension. So if you just search for graph processing max, you should find it. And I can get URLs to folks. Okay, so that's calling that. I did want to show you here, and I've already run this, but you can also run closeness centrality in addition to the betweenness centrality. And in closest centrality here, apparently I actually haven't. Oh, wait. It has an error. I don't know what it's saying there's an error with. I thought I removed that. Yeah. Okay. Not going to show you that here, but the closest centrality algorithm basically produces how close is a node to all the other nodes in the graph, and that's something that's easily done by these extensions as well. And there's betweenness centrality and a few other things as well. So a lot of different algorithms that you can use within Maze Runner, and the graph processing extension has a similar set of algorithms, although it's not 100% overlap. So there are a variety of different algorithms. If you're using Spark, you get the benefit of the Spark community as long as we add support for that into Maze Runner. And if you're using Neo4j directly, it may be faster for smaller data sets, less computationally intensive things. All right, I think that is about it. We're about out of time, so I'll take questions.
And this might be a little naive, but my assumption was, isn't the philosophy of the big data community that you move the code to the data rather than data to the code?
The philosophy of the big data community, move the core to the data versus the data to the core. I think that is a classic argument that gets made with every single computing decision. I've heard arguments in both directions regularly. So in this case, we are putting the data to the core. If you did the process, sorry, in the case of Spark, we're putting the data to the core. In the case of the Neo4j extension, where you're doing the processing built into the Neo4j extension, it's the other way around. It really just I think it depends on your environment and what you are comfortable with. In the case of Neo4j doing all the processing for you, you get to run that on a single machine as an extension. You don't get to run that on multiple machines. You get the advantage of, with something like Spark, of being able to distribute that across a wide variety of machines. I think that's one of those classic debates like Vim and Emacs or VI and Emacs. So, any other questions?
If you're running on one machine, is using Neo4j always faster than Spark?
If you're running only one machine, is Neo4j always faster than Spark? I would expect that it is faster if the algorithms are written similarly, simply because you don't have the export and import process and all of the messaging that's going on, at least with Maze Runner as it's architected today. So I would say, yes, it's probably always faster, but you have the how much are you going to impact production performance issue. And in that case, you might not want to use the CPU of that one machine to run these types of analyses. Any other questions? All right, thank you very much.